So warm welcome to all of you for today's webinar. I think I will start with a bit of housekeeping. Do please note that the webinar is going to be recorded. Do please also mute your microphones during the presentation, and for the Q&A session after the presentation, I would like to ask you if you can please drop your question in the Q&A. And I will read the question and possibly invite you to comment after. All right, so we are extremely fortunate today to have with us Professor Thomas Adams. I will properly introduce Tom in a minute. Before that, I wanted to say a few words about our center, the UKRI Interdisciplinary Center for a Chemical Circular Economy, or CircularChem in short. The remit of CircularChem is to transform the UK's chemical industry into a fossil-independent, climate-positive and environmentally friendly circular economy. We have three main research themes. We have our theme 1 on enabling technologies for circular chemical economy, our theme 2, which I'm also leading, which is on process integration and all systems optimization, and lastly, theme 3 on policy, society, and finance. Do please check our website to learn more about our research activities. And that's also a good opportunity for me to mention that we have recently added a couple of case studies on the website, one on CO2 electrolysis, a second one on green ethylene production in the UK. And I think this will bring me now naturally to today's webinar on techno-economic analysis and life cycle assessment for emerging technologies in a circular economy context. What I would like to say is that this is particularly relevant to the work we are doing under theme 2 on process integration, where we are using a lot of techno-economic analysis and life cycle assessments in order to conduct our assessments of emerging technologies for fuels or greener fuels and chemicals. So I would like now to introduce our speaker, so Professor Tom Adams. Tom is a professor of energy and process engineering at the Norwegian University of Science and Technology, NTNU. He received a dual bachelor's degrees in computer science and chemical engineering from Michigan State Universities. Then he completed his PhD in chemical and biomolecular engineering at the University of Pennsylvania. And then he did a postdoctoral research in chemical engineering at MIT. Tom is a licensed professional engineer, and he was a professor between 2010 and 2022 at McMaster University in Canada. His research focuses on the design, modeling, simulation, optimization, and analysis of sustainable energy systems. Application areas in his research group include sustainability, biofuels, alternative fuels, synthetic fuels, fuel cells, energy storage, hydrogen economy technologies, integrated community energy, and many other kinds of energy systems. And Tom is also the author of two popular textbooks. One is called Learn Aspen Plus in 24 Hours, and the other one is called Exergy Tables. So with this, I would like to hand over to Tom and invite him to give his presentation. Welcome, Tom, and thank you.
Yeah, thanks, Benoit. Thanks for that introduction. So, hello, it's good to see everybody. A really good turnout, and I think I'm speaking to the choir almost with this one. I'm based on your center, so it sounds like what you're doing is exactly what I'm interested in and what I'm going to talk about today. So I expect your questions will be a lot more high level than what I'm used to, I think, when I talk about this sort of thing. My role with this, I'm going to talk primarily about the ISO standard 14076 that's in development. That's the main point of discussion today. So Benoit already introduced my sort of academic roles, but I'm the project leader for the ETA standards project with the Chemical Institute of Canada, and so that brought forward ultimately the proposals to develop what is now going to be ISO 14076. So I'm a committee member with the Lifecycle Assessment Subcommittee for Canada at the ISO, and then I'm the convener of the working group that is building the standard, basically. So we have 21 working group experts from 12 countries that are in this group, and it's basically different member countries can send a technical expert to work on the document itself that would become the formal standards documents. And so that's just the context for where what we're going to talk about today, primarily on ETEAs. And just, you know, a little bit, some more background on what I do. From a research perspective, I'm a chemical process designer at heart. So that's my ultimate training. And that means either designing a piece of equipment or designing a new system out of existing equipment. So the design of the process or the equipment. This requires a lot of modeling, a lot of simulations, because, you know, we have to really understand and value the concept from a, you know, a technical level. We do steady state dynamics, and we don't really design a process. Everything is wrapped inside of an optimization. So we really design all possible processes, and then we use mathematical optimization to help us pick the best one with various algorithms. And all of this is done within the triple bottom line of sustainability. So this means economic sustainability, environmental sustainability, and socio-political sustainability. So every new idea that you have, if it doesn't, it has to have a business case, it has to have an environmental case, but it has to be socially and politically acceptable. You know, otherwise it's not going to happen, right? So you have to think about all of your ideas in this context. And that's really where we end up with ETEA, because you have the TEA, so the economics part, you have the LCA, the environmental part, and together they make ETEA, and then that then informs policy, right? So this is how we can link all these three together. So that's just the background of you know, where my training is and what I do. Application wise, I've been all over the map. I'm not in a very particular technology. I'm more systems in general. A better way to look at what I do is taking technology ideas that might be at TRL 1, 2, 3, and then seeing how they would be commercialized, and they'd work at like 8 or 9 or 10, depending on who, what TRL scale you're using. So at the full commercial side. And so the areas, I'm all over the map. So I'm very neutral. Very often I have collaborators that have, you know, industry, academia with different ideas, new catalyst, new piece of equipment, new process idea, new concept, new supply chain. And so we very often work with them to value that technology. Okay, so what is its value on the eco-technoeconomic analysis sort of side of things? The big picture question I'm trying to answer at the end of the day is, how do we spend the next $1 trillion to fight climate change? Okay, so it's, where do we put our money? Excuse me. Okay, see how this is going to go today. Okay, so I think a lot of you might be familiar with the concept of ETEA. So more, if you're not, we'll talk about that. We also need to talk about why we need standards. One of the, I think, you know, you're familiar with an LCA, you're familiar with a TEA, it's really just the two put together, right? So the eco part is the environmental impacts part. The techno part is the materials, energy flows, efficiencies, how it's actually working. And then the economic part, I think that's very easy to understand. It's not just cost, but it's profitability, it's business case, it's uncertainty, it's risk. Okay, and that's very important in the economics, because risk is a huge part of it. And, you know, interest rate on the loan, debt to equity ratio, that often has more of an impact than the technology itself and the profitability of a technology proposal. So we really need to be informed, and we really need to factor in all of these different areas. And so combining that, we get the ETEA. And, you know, in my line of research and in my collaborations and my consulting, I've worked with a number of different groups, and I don't know where this group comes from, but you might come from all these different sectors. I think industry is a real obvious one, because you're looking at technology selection decisions, you're looking at go, no-go decisions, you know, day-to-day process design decisions, if you're making a plan or you're making operational decisions. You know, at the end of the day, it's a really obvious one. But one that's less obvious is in capital finance, and this is becoming more and more important. actually, as we get into the realm of green financing. So if you're investing, you might loan $1 billion towards some large capital project, and there's a green aspect to it. With the environmental, maybe it's just CO2 emissions, or it's specifically a higher risk green technology. It's really important to have that ETEA in place so you can value, the environmental benefit, which especially in green finance means you might accept a higher risk project, that you wouldn't otherwise, just because of the potential environmental benefits that are accounted for. Funding agencies are another one. This is one of the first groups to start this, because we're looking at assessment of merit of a proposal. Okay, so you want to invest in CO2 capture research. Okay, what are the technologies? Where should my research funding go? Because I'm going to get sort of an eco return on that funding. So it's really important to have these cross-cutting comparisons. You'll see in Alberta, Canada, for example, so that's the energy producing province primarily in Canada. Some of their proposals, they actually will tell you to do an ETEA with very specific parameters because they want to have a cross-cutting comparison of proposals. All right, so this is really one of the key users in that sense. And then, of course, academic research where I'm located. And these are the things I use it for all the time. But what's really important to me is speaking the same language across academic groups. And that's really the number one value that I think in terms of all of these things is how do we all talk to each other in the same language? And I'll explain more of that in a minute. Then there's a question of why do we need the ISO involved? So the kind of standard, this we call a technical specification. There's different frameworks. It doesn't matter so much, but in their language, it's a technical specification. The main reason we need it is that we really don't have a systematic way to compare technologies between either different processes or especially between just different author groups. You do one study, I do another study, and I can look at your numbers, I can look at my number, and I can almost never really compare them. Just like take your number, sit it next to mine, and say, well, your cost is lower, you're better than me. I can't say that. There's so little consistency. So it's really hard. I'll show you a little bit about that in a minute. Another one, if you see this in the literature, so we have, if you're into academic publishing, we have a concept called the negative result. The negative result means your idea didn't work. And in culturally speaking, it's hard to publish a negative result. It shouldn't be, but it is. So what happens if you have an idea that maybe it's not so great at the end of working on a year of research, you still compare it against something else that makes it look better, right? You can always find something worse than your idea to compare it against. So you have all these straw man arguments. You can find 100 papers in literature of technology, and every single one says that their idea is the best. That's not useful. Okay, we can't make those kind of big picture decisions around that. And it's because we have lots of variations in how we do things, the strategies, methods, and ideas. I'll talk about these kind of things, but when my idea versus your idea, it really matters the location. My idea might be fine in one place, yours might be fine in another. How we define things like efficiency at all, things just key performance indicators, lots of things that go in the analysis that turned out to have a huge impact on the bottom line. So at the end of the day, there's so much noise that you get no signal out of that noise. You can't make any really good comparisons in the literature between things. So this was the original problem, is just understanding differences between things and making decisions. So here's a simple example. So we had taken surveys of ETEAs in the literature of different, in this case, we're looking at power plants with carbon capture. I've just taken 3 here this is like a classic coal. This is coal with oxyfuels and coal with gasification combined cycle. So 3 strategies of making power with coal. All of them have carbon capture and sequestration. So they're all meant to be like a reduced impact coal. 44 studies in the literature, taking the numbers that are reported directly. In this case, we're looking at cost of CO2 avoided. I'll talk more about that as well. Cost of CO2 avoided is basically the extra money you spend to be green. Okay, so this might be euros per ton of CO2 avoided by doing the green thing. So you want a number that's low. Okay, if you're going to invest in a green technology for the purposes of avoiding emissions, you want that number to be as low as possible. Okay, but it just as reported in the literature of all the different technologies, they basically average out within statistically insignificant differences, okay, in terms of error bars and things like this. So you can't look at the literature and make any meaningful conclusions really between them. But if I just take the same exact technical information and all I do is I standardize on things like size and supply chain and location and year and things like that, but I don't change anything about how they did a cost. I don't change anything about the technology itself. We actually get a very different picture once we standardize. And in fact, it's very different. So they're all statistically significant. That means they're outside of zero bars here. This one's really significant. And now we have useful information that we couldn't see clearly. And this is something that would have been really nice to know a while ago, because in the States, they built 2 of these plants, total of 20 billion US dollars. And then in both cases, after building it, they switched it over to a natural gas power plant, because even after construction, it was so expensive to operate that it was still better just to switch to natural gas and just leave $20 billion as sunken cost. Okay, like that's a boondoggle that we could have just seen just by taking the same information we already have and just looking at them in an apples to apples comparison. So these are some really good examples of why we need it. And you can kind of drill down the details. So here's another example. Let's say I have 2 power plants of that type and they're at different sizes. Okay, their sort of cost of electricity is about 6% just from the size. Okay, so 550 to one that's half the size. But if I have 2 different plants at the same size, okay, using that same kind of analysis, but they're all standardized, but they're the same size, their cost difference might be also the same percentage. And basically in this example, it's just a really short way of looking at it, but the effective size has as much signal as the actual technology itself. So if we're not even able to like make comparisons on size, if everyone just does whatever they like when we're trying to make technology assessments, well, we're just blending out the real signal. Like this is a signal, okay? I have a real piece of information here, and this is noise. So we need to blend that out. We need to get rid of that. But the problem is we do this all the time. Okay, the reason I'm using this example, because at least in the power plant world, it is very common to do a study. Okay, I'm going to look at my power plant without capture and my power plant with carbon capture. Okay, and this plant is smaller in total net power because what they do is they take the same plant and then they add a CO2 capture section. There's a huge parasitic load and the net power is a lot smaller. Okay, so let's say I go from 750 megawatts down to 500 net power because I have 250 megawatts of parasitic load in my CO2 capture. These are standardized on the same fuel input. Okay, but this is just a really simple question of, okay, but I want 750 megawatts of power. I don't want 500 megawatts. I still need 750 megawatts of power. So unfortunately, we do this all the time in the literature. We have the same fuel input, and it tends to be for convenience. But the LCA people, they don't have this problem. So they use the concept of functional unit, and I get the sense there's probably a lot of LCA people in the audience. Right, and these are really based on outputs and outcomes. So these are based on outputs and like outcomes. Okay, and so that's been recognized, but our per unit costs are sensitive to size. Okay, and so when I talk about cost, size really, really matters because they're nonlinear. Okay, so the economies of scale are a huge, huge factor. So when it came to ETEAs, when this started being developed, it was the sense of we need to take this kind of functional unit concept applied to the LCA and apply it also to the TEA. Okay, and that's really one of the major development points. So let me give you an example of when we do this now. All right, I'm going to give you a little bit more of that power plant study. So in this case, we looked at over 100 different studies that had some kind of published ETEA report on a power plant that had carbon capture. Okay, and what we did is we took all that information and we rescaled it to the same net power output, leaving the gate. Okay, so we have to adjust cost based on size. We did it all at the same time and place. That's something that's not common either. So, we picked 2016 in this study. It's a little bit older. And we looked at the location in North America. So if you had a plant for Germany, a plant for the UK, we could adjust its location with the purchasing power parity index. So what it would be to build that same plant in the United States. We then took the same supply chains for fuel. So the same life cycle impacts, the same costs. We looked at the CO2 capture. The CO2 capture needed to be at the same pipeline conditions, at the same capture rate, the same purities and pressures. We took the same life cycle assessment methodologies. We took the same standards for things like NOx and other kinds of chemicals and emissions along that entire life cycle. And we can use that to compute things like cost of CO2 avoided with the same baselines. So just we took the same information in the literature and we standardize it. Okay, and we get a plot like this. And we call this the plot. It's very popular. We're constantly updating this plot. Here's our most recent version. Okay, what we're looking at here is the cost of the greenhouse gas emissions cradle to gate exit. So life cycle up until electricity leaves the plant. Okay, at grid quality. We want this to be a zero, as low as possible. And this is the levelized cost of electricity. So we want that to be as zero as possible. So we want to be down here in the corner. And then every point is a research study, okay, that we have standardized to that set of conditions I just told you. Now, when we first did this and we didn't have standardization because we didn't even think about it at the time, we just set out to do this, it was just a cloud of nonsense because everybody was all over the place. And there was absolutely no useful information I could gain by taking 100 points in the literature and comparing them together. But if we just adjust for like the noise, the external factors, the things that aren't really about the technology, they end up falling into these really nice bubbles. And these purple X's, for example, this is coal, like a classic coal power plant with carbon capture with solvents. Okay, so something we already do in Canada and other parts of the world. Okay, we already know how to do this. But they all fall in the bubble. And this noise now, these are different authors, different solvents, different assumptions around their own method and their own methods for computing cost. All sorts of different technologies and things happening in there, but they all fall into a nice bubble, right? They're well contained. And so we've eliminated that macro noise. And now we have like real information that's communal across many people. I mean, there's a collective agreement. It's remarkable. And then we look at things like a green diamond. The green diamond is the same thing, but we have a membrane instead. Okay, so that says, okay, it's very similar to solvents that we already can do, but we could get a little bit better. This is how much better we think we can get. These are membranes that don't exist. They're fictional sensitivities and yields. So this is about as good as it will ever get. So now I have an existential crisis question. If I'm a funder, should I spend $1 billion to do research here if we can already do this now? Okay. Other things are like IGCC. Okay, that's the gasification one, blue circles. But the first really big improvement happens here at oxy-fuel. So either coal or natural gas. So this is oxy-combustion. Okay, it has a bigger area, but it's clearly outside of these ovals. And now you have a new paradigm. This is chemical looping combustion from coal. There's not enough data for gas to have it. But this is natural gas combined cycle with carbon capture. This is something we already can do. Now, these economics are probably a little bit more expensive now. This whole thing would shift over to the right. But it's all the way down here. And there's another existential crisis question of why would we do research here when this might be a lot easier to do, at least in North America. And then there's other technologies like solid oxide fuel cells and some waste to energy things. We just keep adding points here as we find them. But this is the power of the ETEA because we can, when it's standardized, we can take all the noise from the communal effort and just remove as much of that as possible. And we finally get the signal. We have the benefit from all of our combined work, and we can use that to make really important decisions. Sorry about that. So that's where this was born. That's where the standard movement was born. It was out of this kind of stuff. It started. All right, you're doing great. You're doing great. We'll get through this. Okay, so it really started in the beginning. The DOE, U.S. Department of Energy, started building internal standards for their own TEAs, and they sort of recognized this noise problem. And so they started publishing documents in 2015, basically saying, okay, everyone that does a study at the DOE, we should have this exact assumption. All right, it was a good start. And that actually laid the groundwork for a lot of the standards that were developed later. So the stuff I just showed you was from our group in 2017, but working in completely independently and aware of each other was a a group of universities in the US and the EU that were also proposing an ETEA standard methodology and sort of developing the principles. I think their biggest contribution that really stuck is really connecting the LCA 14040, 14044 functional unit thinking directly to the TEA. Okay, and that's what's really made it into the 14076 that's coming forward. So this was done independently, kind of at the same time. And then these people all got together at a conference at FOCAP-D 2019, and we put together a formal call to develop the standard. And so that's really when it went into play. And so we've been developing this since 2019 now. But the point is, and there's been some other groups looking at these same issues, but the point is that we've all been working, even working independently, we kind of all came to the same conclusion that we really needed a standard like this. We really needed to find a way to get rid of that noise and talk to each other on the same basis. And so that's where the 14076 progress has been made. In addition to the 12 countries that have sent 26 working group experts to develop it, we have a large number of supporters that are outside of the ISO. From academia and industry and government. Okay, and so these are all people that have sort of written letters to champion the cause and just, indicate the need for this kind of study. So we're not operating in a vacuum. Many of them have actually sent members to the ISO or have informed their own local bodies about it. Okay, so the draft itself of the text, I can't tell you until it's released. I can tell you about the strategy and some of the key points that are relevant, I think, for this discussion. So here's our big picture view for how it's going to go. The 14076, this is called Principles, Requirements, and Guidelines. Okay, so it's basically how to conduct an ETEA in a general sense. All right, so sort of best practices, but also requirements. So it has something called a shall clause. A shall clause means, like, if you're going to do an ETA that meets the standard, you have to do these things. And if you don't do one of them, it doesn't meet the standard. Okay, and that's just how standards work. Now, this is really about the methodology. It's not about numbers or specifics. So a person who's going to do the ETEA would use this methodology, but we do not tell you, okay, your power plant has to be at 550 megawatts to do your study. It's not like that. You pick your own assumptions, but the idea is, if we're all going to be talking to each other for the purposes of sort of general technology evaluation and comparison, you should be picking parameters that are well defined that other people can also pick. Okay, so this could come from a government funding agency, it could come from a company, it could come from a researcher, it could come from another ISO report. Okay, so this would be defined in something called a parameters document. It's just a list of assumptions that everyone should follow. Okay, this should be your project year. This should be the currency. Right? Something that keeps everybody on the same page. And then we'll have a second ISO technical specification that basically defines how to make these in a standard way, so that we have a standards ecosystem by which each individual organization or interest group or agency or whatever, they can put out their document and everyone can follow it, and then we can all be on the same page and all talking the same language. Okay, so that's really the vision. Okay, and this is where we are right now. So I'm just going to repeat again, we do not tell you any particular choice of assumptions and parameters. It's really about communication and the methods. So the draft has been written. It's still confidential because it's not approved yet. We went through a public consultation period, and now it is circulating among the member countries for formal content. So there's 30 something on the full committee, and they can each have their own internal evaluation. But I can give you the abstract. I'm not going to read it, but basically it's about the methodology, it's about best practices, it's about the minimum requirements that you have to do to make it meet the standard. It's about communication, that's really important. And it's about, it can work for really any process system at any size or scale. Okay, so it's very general. It's not for a particular application. I think I'm going to skip the general structure for the sake of time, but the key point is that we need to introduce definitions. We need to worry about the framework and the methods and the requirements. We have some illustrations and examples. And also, just for LCA people, the LCA part of the 14076 is really just 14040, 14044. So that language comes directly from there, and sometimes it just refers to it exactly. So if you're familiar already with an ISO LCA standard, this is going to just be the extension really to TEA. Okay, and that's really what's happening for those of you familiar with that side of it. I can explain the basic concepts in, I think, 2 images for how this is going to work. We have our LCA and our TEA, and in any methodology that's like this, it's very iterative. You kind of move from and making decisions around different sections. So you have your goal and scope, just like your ISO 14040 stuff, but now it includes TEA in that goal and scope. And of course, you're going to be reinterpreting and changing things as you go. And you could use it and apply it and go back and make more changes and so forth. It just really shows you it's kind of an iterative, fluid process that's to meet the needs of your own analysis. But I think the really new thing is this image here. So the LCA community will be very familiar with a diagram like this, where I have a product system boundary to conduct a life cycle assessment. And so within a product system boundary, this is normally or ideally like a cradle to grave boundary. All right. And inside the boundary are all the different processes in a supply chain, including the raw materials production, use of energy, making a product, including the factory construction in its end of life, the use of the product, and then the waste handling. Okay, and it's very normal to look at this with an LCA, and if it's cradle to grave, you really only have elementary flows coming in and out. Elementary flow is just something that comes to or from the environment. So I might be pulling iron ore or out of the ground, or raw natural gas out of the ground, let's say, and then my flows back to the environment might be carbon dioxide emissions and polluted water and things like this. All right, so this is my interaction with the environment. But what's new here is what we had to name the business unit boundary. And this is the techno-economic analysis boundary. I think a lot of people do TEAs without ever using the word boundary or ever defining it. But it, implicitly, it almost always means the costs to me or the costs to my company. Okay, so it's 2 different perspectives. We have the sort of the life cycle perspective from the whole supply chain of what we're doing, but we're only acting within a limited sphere of influence, and we only worry about costs within our own limited sphere of influence. So we really have to recognize 2 very different ways of thinking and doing the analysis when you put these 2 together. This is the trickiest part. I think this is the hardest for LCA people to understand the TEA boundary. And for TEA people, sometimes they have to also learn to understand the full supply chain as well. So both communities have to kind of bridge this gap to understand how putting the 2 together is going to work. So the products, this is the same thing I basically just said. The product system boundary is environmental. One of the ways to think about the business unit boundary, it's really the techno-economic boundary, but it's really the business unit. It's the areas of the supply chain that I can directly control, not indirectly control. Like I can control how I make my product. I cannot control how, when I purchase a material, how that supplier made that material, not in any direct sense. Okay, so I'm concerned about my cost, my company bottom line, or my consumer issues. Okay, and so this is really key because this is not a life cycle cost. All right, life cycle cost would be the whole life cycle. All the whole society is involved. This is the business unit only. All right, and then that's really, really key. And we really need this because of that sphere of influence. And this makes a lot of sense because what I'm really interested in is how this technology is going to grow really in a free market setting. Okay, so we have to recognize that each business influence is going to act in its own self-interest. It doesn't mean selfishness. It just means whether it's a person or a company, they're going to do what's best for them. And, they have ethics and morals and things like this, but we codify this in law as fiduciary duty if it's a publicly held company, for example. Okay, so this is just a normal way of understanding how, businesses and individuals can work. But we have to recognize that the individual decisions I make affect the entire supply chain from the environmental perspective. So we really need that. We have to connect the local business economic interests with the global environmental impacts. At the end of the day, the ideal situation All right. If I'm going to give you a green technology, I have some new technology idea. I think it's really good. I want to develop it. The best case I can make is one where every unit, every business unit along the supply chain has a good case, right? If there's a good case for like units 1, 2, and 4, but the third company involved, it's destroying their business model. This probably won't take off as a technology, okay? At least without a lot of major changes. So what we want to do is to come up with a technology where each company, each business unit or person naturally chooses it. They choose it because it's a good idea for themselves, but for the whole society, we have a collective global environmental improvement. That's what we want. Okay, if we can, these technologies naturally adopted, we can have real change without command forcing. Okay, that's what we want. So that's the ETEA really helps us do that. Okay, but it's tricky because we have to understand scale. And this is where this is a departure from the LCA set. So in the LCA world, they have a concept called a functional unit. And we have the same concept in this one. All right. The functional unit is, I'm not going to get into all the details, but essentially you think about the purpose of what you're doing in a per unit sense. Okay, so like per kilogram of the product I consume, per kilometer that I drive something, per hour I perform a service, or service has been performed, whatever. Okay, and the idea is that the environmental impacts are basically linear. Okay, so if I have double the use of my product, I will double the life cycle impacts. And it's not always true, but most LCAs have this assumption completely built in, and a functional unit almost requires this by definition. But economics are nonlinear. Okay, so scale really matters. So we have to have a new term that's called the basis of production. And I can't, the definition will have to still be approved because it's still in the draft stage exactly. But you can think about it, it's really the expression of the functional unit at scale. Okay, so my functional unit might be, CO2 emissions per kilowatt hour of electricity. But at scale, my base of production might be, well, my power plant is 250 megawatts net power, always running for 30 years. Okay, so it's how do you achieve your functional unit at scale? But your scale could be defined like this. It could also be defined economically, and I don't want to get into that detail. But you can have scales that are things like, $1 billion of investment. That's my scale. That can happen. But we don't need to worry about that so much. But you have to do this because when you're comparing processes, they have to fulfill those same functions. Okay. And that's one of the key things that had to be worked out in the new standard. And I think that's the most new thing. Okay, so but the whole point though is if we can do this, then now we have the standardized decision tool to evaluate these impacts, different solutions when applied in practice. So then we can all speak the same language. Okay, so that's the point. So let me give you just a couple examples to put things in perspective beyond the motivating ones I showed earlier. So I'm going to go back to cost of CO2 avoided. I use it because it's probably the most well-known ETEA metric. Like you have to do the ETEA to get it. Okay. Basically, you might hear things like cost of CO2 abated or cost of CO2 mitigated or avoided. They're all going to have some nuances and arguments about how to define them. But a very general way to think about it is some extra cost you spend to do a green thing that you wouldn't normally do, divided by the emissions you avoid by doing that. Okay, so for biofuels, for example, let's say I'm going to use biofuels instead of a petrodiesel or a petrogasoline or something. Okay, so I have my cost of the biofuels minus my cost of the petros, and this should be usually higher. Okay, and to be more specific, I usually am concerned about the cost to the business unit. So if I'm the customer, I'm usually concerned about my own cost, not necessarily societal cost. So what are my personal costs when I go to the station and I get to choose what fuel to put in my car? Okay, that's my business unit. There is me. And what are my costs? And then, compare that to business as usual, which is my cost if I bought the diesel. But on the denominator, it's the life cycle difference. So I actually care about the full life cycle because my decision to pick pump A versus pump B actually has complete life cycle impact. So that's my responsibility. So I have to include it. And example units might be, pounds per ton of CO2 avoided. So it's 50 British pounds per ton of CO2 avoided. That's a really nice number. Okay, that's a nice low number. That'd be a good technology choice there. Okay, so we're looking about eco returns on my money. If I'm going to do this green thing, what kind of eco return do I get? I want that number to be low. Related to that, you can have a life cycle cost of CO2 avoided. It's going to be basically the same thing, except now you're looking at the full society cost, not just one of the business units. Okay, very, very similar. And all this information can come from an ETEA at some level. Okay, so let's say I just have some process. Okay, I'm going to produce some product and it's going to be used for some purpose. Okay, maybe it's driving my car. Okay, so in this supply chain, I have many different business units involved. Okay, so I might start from raw materials production. I might transport it. A different company would then convert that to something, a product that's purchased by the consumer. And then there's some additional waste, and this could be known waste treatment, but it can be hidden costs in society too, which are kind of fuzzy. But the point is that there's more downstream. This green box is the environmental boundary, so the product system boundary, and then we have emissions and materials coming in and out of that boundary. Now, costs are always passed down to the consumer, really passed downhill. That's just something to keep in mind. But when you use a metric like this, we can use a cost of CO2 avoided at each business unit. So I could have a cost of CO2 avoided to business unit 1. So what are their extra costs involved in this green technology change that I'm thinking about? Okay, maybe it's like nothing. Maybe they don't change anything, so it's fine. They don't care. Or maybe it's something, wow, they got to clean up their product a little bit more. It meets a different product purity specification or whatever it might be. Okay, and I might have one for this one, and the denominator is going to be the greenhouse gas, the portions of that life cycle for which they are responsible. And I might do it again for number 2. And the same thing, they have their business unit boundary is just this box, their own costs, but their denominator is actually be what they're responsible for, which is going to be more business unit 1 and 2, and maybe some other things too. All right, and we can go down the line and we can compute one of these for all of them. For unit 4, the customer, very often we just use that when we make a decision. Well, what's the final customer CCA? All right, and that's thinking a little too shallow. It's a good one to use, especially because you can incorporate things like wastewater treatment, like disposal fees and emissions fees or something into that and pass that cost back to the customer. But it's a little incomplete, okay? You could do one for the 5th one, which is, everything else. That's not the same as life cycle cost of CO2 avoided, because that would be the full society cost divided by the full emissions, okay, on the whole boundary. So that's something to think about. But if the technology is good, if it will work on its own, then all of these CCAs should be small and the life cycle. All right, that's what we want. That's the golden goose, right? It's not enough to be just one because we have to be concerned about everything. But if we can get all of them low naturally, then this is the technologies that are the most promising that will be adopted on a free market without coercion, or maybe a small carbon tax. Okay, you might need those kinds of incentives. Or small incentives or something, but we want these to be small, and we have to be thinking because these are individual self-interested people. That's where 14076 I think is the most important, because it really breaks it down into all the pieces and for all the things that we really need at the end of the day. I think I'm going to leave it with just maybe one more quick example, but another example that's with real numbers might be, should I electrify heat? Okay, this is a really hot topic in the EU system. They have a lot of funding available for that, answering that question. Should I switch from burning a fuel and using electricity to heat stuff? It could be your house. It could be extremely high temperature chemical reactors. Okay, so we can look at that answer at a very rough sense by looking at the CO2 emissions of different power sources, and these would be cradle to product. So I just collected a whole bunch here from different sources, and these are some rough averages for some things like coal power. The countries, we are actually pretty well-known data. Modern natural gas is here. World average is here at 438 grams of CO2 per kilowatt hour. Germany, US, coal with carbon capture is here. UK coming in just a little below that. We have some of the blue ones. These are all carbon capture technologies with fuel. Canada, we're getting pretty low here, just about the same as solar with batteries. Natural gas combined cycle even lower than solar with batteries, so think about that. And then we get down to think Norway is lowest in the world. It's because it's almost all hydroelectric, which is the very bottom end of the spectrum. Okay, so it's a huge orders of magnitude, 2 between the top and the bottom end. Okay, so that's our data because it depends on the source. So let me ask the question more specifically, should I do it in Norway? Okay, because I'm sitting here in Norway and I'm going to answer the question for Norway. So what I've got here, some other data, I've got the cost of utilities as a function of their temperature. These are sort of average dollar per gigajoule of service per different average chemical plant utilities. We have refrigerations, different kinds of steam. Okay, so for medium pressure steam, it's about $6 per gigajoule of heat as provided by condensing steam. So that's about 180 Celsius or something. All right, and I can look at the price of electricity in Norway. It's about $32 per gigajoule. That's the average price for last quarter that I have data for. And then if I was to produce steam from natural gas, I have some emissions and versus steam from electricity. Okay, so I can come up with these numbers through various ways. I can compute the CCA pretty simply. I'm just going to do unit conversion here from dollars to gigajoule to dollars to megawatt hour. And now I can compute my CO2 emissions. So this is my higher cost of electricity minus my lower cost over my higher cost of steam. Okay, this is my emissions minus the emissions of electricity based steam, which is very low. It's about $470 per ton. And that's at the medium pressure level. Just to give you some other numbers, this is 100% efficiency direct heating. If I used a heat pump, I can probably bring it down 160 to 240, but I could go down lower in temperature. So I can lower pressure steam is lower cost than higher pressure steam. Okay, so I have some numbers. So the question is, okay, those are the numbers. Should I do that? What should I do? Should I spend my money to do those things in Norway? Okay, so I just pulled a number of other types of things I could do with my money to avoid CO2 emissions. All right, here's 2 really good numbers to reference. One is capturing CO2 from a coal power plant, sequestering it. Okay, we do this now, $50 a ton. It's like one of the cheapest things you can do. And it's also basically the carbon tax in Canada right now. I think it's like $1 higher, something like $5 higher in this one. I'm not sure, very close. All right, so it's a really good baseline. Ideally right now, everything you do should be less than these numbers. All right, well, here's some other things we could do. I could just bulldoze a working power plant and build a natural gas one right next to it. Okay, that's 90. And that would be not recovering any value of the coal power plant. That's actually just shutting it down and building a new one, losing all sunken costs. Okay, that's a little ridiculous, actually, but it's a lot cheaper than all these other things, like 3rd generation biofuels. This is the best I can find in the literature from butanol. 2nd gen biofuels is the 500. Corn ethanol, gasoline, USA, terrible idea. Waste to energy, there's all sorts of projects. I picked one for Norway that I have data for that we've done, 1,300. So the heat's in the 200 to 470. Okay, so for Norway, well, we don't have any coal plants to knock down, and biofuels aren't ready yet. So, it's not terrible, but I wouldn't do this in the US. We have a lot of other options here, especially, okay, that we can do. So it really depends on where you are, but now we have a really good perspective on things that we can do. Okay, and that's what I want to be able to do with the ETEAs. I'm gonna stop it there. I think for the sake of time, I just wanted to say we're working on doing the same things for hydrogen as well. These are not standardized, so that's what we're doing right now. We're trying to give you the same kind of information for the hydrogen economy. It's a big undertaking, so that's what our active role is right now. Okay, and I'm just going to skip right to the end. And my main selling point is, this standard, we think we can help across the board with academia, with industry, with finance. The main thing I want you all to do is talk to each other better so that we can learn from each other. That's the motivating factor. Okay, and that's so hard to say. And actually, so hard to actually do. I can say it, but it is so hard for me to look at your papers and your work and for me to compare it to mine and to compare it to each other. But if we can just speak the same language, our value together is magnified greatly. All right, thank you very much.
Well, thanks very much, Tom, for your presentation. It's a lot of the things you're saying is also music to my ears. It's really nice to hear, and then I think you're making a great point for using ETA in general for guiding research and development and policy. I think, you know, it's, I can also see that it's really relevant when, you know, you're trying to reuse some of the published results in your own assessment without having to redo everything yourself to get consistency. And I think that's another benefit. And the effect of scale that you're mentioning is something we see throughout. And I think in some of our recent assessments, LCA, we're saying, you know, functional unit might be, say, you know, 1 ton of, say, ethylene, but for a plant that's producing, say, 100 kilotons per annum or something like that. So it's you know, your standard is going to bring that together very, very nicely, I believe. So I cannot see questions in the chat at the moment. So I'll keep, you know, I'll keep bugging you with some of the points I noted, and you know, if anyone wants to ask a question, please do use the chat for that.
Yeah. I just want to interrupt really quickly. So you had said your standard, but it's not mine. I want to make that really clear. I just want to make it really clear because this is an international body with many people participating in this. So I want to make that really clear. Yeah.
I have a comment from Katie, who's saying that she's, you know, she's really sold, and there's no question, but it's just a comment. One of the things I noticed on one of your slides is about the, you know, about the boundaries, and you're making a point that the LCA boundaries and the TA boundaries are, you know, are not necessarily the same. My understanding was even in LCA, it's common to distinguish the background system for the foreground system, and the foreground system corresponds quite well to your business case.
Yeah, I think in the common lexicon, the business unit are direct impacts, and then everything else is indirect impacts. I think that would be a really good way to look at it. So when you say foreground or background, I think that would be the same thing I would say. I just don't use those particular words. Yeah.
Okay.
Yeah.
I also noticed that in the standard, or at least in the supporters in the standard, the UK are not necessarily very well represented. So I think we could do a better job. Is there still an opportunity for supporters to, you know, to chip in, or
yeah, I mean, this is going to be, I mean, it's 4, I think it's 4 years formally. I think it was 2 years since it took 2 years to get approval to start, and then 2 years to formally start. Even though we're in the draft approval stage, let's just say that just like every country approves it and it's done like that, but we still need people to develop, to maintain it. And we need people to develop. So I think I showed the big picture where you have like the first one is the methods, the second one is this parameter, it's the communication aspect of it.
Mm-hmm.
Right? We still need to develop that. It needs to be reviewed every 5 years. And so we need lots of experts. I will say we are short on the TEA experts. We have many LCA experts, but it's very hard for us to attract good TEA experts. This is just, the reason is because we're in the LCA part of the ISO. Okay, so we had to pick a home. There really wasn't a TEA home. So the LCA became the home for it, but it's harder for us to attract people that really understand the business side. So I'm, you know, in my own line of work, I'm used to working with TEA people and teaching them how to do an LCA. It's the opposite. I need to talk with people that know LCA intimately, and then how do we bridge that to economics? So I need definitely more help with TEA. And the way this would work is if you were to join, you have to contact the the standards body for the UK, the one that's approved to work with the ISO, and basically apply to become a member. Okay, and so I can show you how. I cannot be involved. I can basically point you to the right person to email, and that's what I can do. But you have to join. Each country has their own approval process because you have to be formally vetted, and then you are appointed to a committee, and then you have to be named as a working group member. But in my experience is most standard bodies, if you are actually interested in working on it, it's a fast track because I think they have a hard time getting true experts into things. So if you really want to participate, you can email me separately. If you don't know your own standards body to contact, I can show you what to do. And you can join at any time in the process and remain on the committee for whatever appointment duration you have.
Okay, thank you, Tom, for that. Yeah, we might email you. I have now quite a few questions in the chat. Sharon Velasquez-Horta asking you, she says, I was wondering how you do consider the scaling up of the systems And she has a further questions down and says, how do you give information on how to conduct the scaling of systems? Is that part of the?
Yes, okay, I can comment partially and partially. I cannot because of confidentiality, because I have to like walk this fine line about the actual text of the draft. I can say that in my line of work, our scale up has been scaling non-fuel portions of like basic capital using power law relationships, and the power law scaling factors are based on, actually there's a group at Princeton that produces cost curves where they try to suggest how you scale things up in different kinds of technologies. So we actually use their guidelines for doing scale up, and that's at the research level. At the standard level, the standard will suggest a power law strategy, but you have the power to change it. So it's more like you have to pick something, however you do it. If you are going to change other people's work to your own, there's a best practice for that. However, if you're just doing a cost assessment at your own scale, it's up to you to cost that with your own methodology. So it's kind of a wishy-washy answer. That means the ISO standard has like, you should have a method and tell us to us. And then other people might define what that has to be if you're going to follow their method. I think that's the best way I can put it. So there's a difference between a standard and then a best practice. And I think best practice is a power law relationship if you have no other information.
Right.
Yeah.
Okay. Okay. Another question related to countries, but from a different angle. I have Paula Bianco asking if it would be good to hear your advice on applying similar methodologies for different countries and the challenges that are expected. Is that something you can comment on?
I would, okay, and actually this is one of the partnerships where I'm trying to partner with different people in different regions of the world, because even just for the power plant, we have a fantastic data set. All right, with this fantastic data set, we've standardized, we've kind of normalized, we can reapply the baseline assumptions. Okay, so for example, everything I showed you was North America. Well, we know exactly how to move that to the UK, right? Because we can use different tools, and actually our standard does have best practices for geolocating. That's actually our existing ISO standards already exist for that. So how do you take estimates from one country and move them? You just move them differently now. We're just going to move them to the UK different. So you would select, for example, like what you think is a better cost for fuels. Supply chains would be different for your country. The baseline of comparison would be different for your country, but like the methods are all there and the starting data set is there. So what I have is low-hanging fruit that if you partner with me for your own country, your own region, your application, you can work with me, and I think we can get a lot of results out of it. So I've been doing that with power. I'm doing this with other things, not just power, but not just CO2, things like water impacts, safety impacts, actually. So we look at more than just cost. We're actually doing like risk to the people in the community affected by things like a carbon capture system or a pipeline. We look at other kinds of things like not CO2, but water. Okay, what are the other environmental impact trade-offs in the same kind of structure? So we have a lot we're doing. And if you are interested, man, come to me, because I got data that's like low-hanging fruit to get started. Yeah, for sure.
Okay, thank you, Tom. I had one final question. I see, I think I've been through the chat, and one question I had is connected to some of the work that some of us in the center are doing on also trying to connect social impacts to economic and environmental impacts. And I think it's Peter Styring and his team who were making the point that we could also use the same inventories to quantify the social impacts. Do you see a possible extension maybe later in the future for
okay,
this kind of social LCA into
I'm trying to think what I can tell you is, okay, I'm not a social side expert, so I can say I have no expertise on that. Okay, I listen to social LCA. However, there is a body of people that are trying to standardize that as well. I don't know a lot about it. The general methodologies like if it's an impact fact, if you can treat a social impact factor in the same way you can treat any of the other environmental impact factors, then I think the parallels would be very, very similar. But I'm hesitant to go farther because I don't know enough about the social LCA side to know whether it's a good idea to even do that in the first place and how much we can do it. So I just don't have enough personal insight.
Yep.
Answer well there. Yeah.
Fair enough. Well, I think, we're 2 minutes past 1, so we've used more than the 1 hour, and quite a few people have already, left us and extended thanks for your, very clear talk, Tom, and I will join them for that. I think maybe we can either clap virtually or unmute ourselves to clap, Tom. But that was really insightful. Very grateful for your talk today, Tom. Thank you.
Yeah, my pleasure.
And then I look forward to seeing you next week.
Yeah. All right. See you in London.
See you in London. Take care.
right.
And thank you everyone for attending.